Okay, we are diving straight into a really fascinating paper today. It's a new theoretical framework that aims to drag classical information theory into the age of massive real-world AI.
It's a big one. The paper is titled From Entropy to Epiplexity, Rethinking Information for Computationally Bounded Intelligence.
And it really is a major correction to how we think about information or, the knowledge that's actually embedded in data.
Exactly. For decades, the theoretical gold standards have been, well, Shannon entropy and Kolmogorov complexity. The problem is they both assume observers with infinite computational power.
And we, or I should say, our neural networks and LLMs are definitely not infinite observers. They are computationally bounded.
Which means the information they can actually extract needs to be measured differently. So this paper introduces a new measure, epiplexity, which they call $60.
Right, $60. And it's a formal way of thinking about the structural information that a bounded observer can practically learn and then reuse from a data set.
It's the knowledge you can actually internalize and compress, given a time limit.
And just by adding that one constraint, the time limit, the framework suddenly resolves some of these deep contradictions that AI practitioners have just had to accept.
Like the first one, it proves that deterministic processes, think AlphaZero playing itself for millions of games, can actually create new information for a bounded observer.
Which feels intuitive, but was theoretically messy. Second, it shows that the total information you learn is, and this is key, dependent on the order you see the data in. The sequence really matters.
And the third one is the biggest conceptual leap, I think. It shows that likelihood modeling isn't just about mimicking a distribution. A limited observer, just trying to predict what comes next, can be forced to build a program that's way more complex than the simple process that generated the data in the first place.
And that right there is the theoretical basis for induction and emergence.
And the really practical takeaway here is that you can estimate epiplexity directly from training. For example, just by looking at the area under the loss curve. And they show it tracks directly with better out-of-distribution or generalization.
So it gives us a real theoretical handle on data selection, which is where all the action is in modern AI.
Totally. That shift is just huge. For years, the whole conversation in machine learning was model selection. We obsessed over architectures, right? The residual connections, the normalization layers, all to fit a fixed distribution a little bit better.
But we've kind of hit a wall there with diminishing returns. Now, for AI to get more general, we all recognize that it's the data, the quality, the composition, the breadth that really determines success on tasks you haven't seen before.
If you want generalization, you have to fix the data, not just tweak the model.
But we've been flying blind, theoretically. Our existing information theories give us almost no guidance on quantifying the intrinsic transferable value of the data itself. Why is one data set better than another for OD?
Because the classical definitions just don't account for the reality of compute. Take Shannon entropy. It only works for random variables. A sequence from a simple deterministic rule, like Conway's game of life, has zero Shannon information.
Which is just wrong. I mean, obviously, learning the game of life requires acquiring information.
Right. And then you have Kolmogorov complexity, dollars. It's elegant, sure. It's the length of the shortest possible program that can output a string, skitty.
Beautifully objective, defines information perfectly.
But it's totally useless in practice because it's incomputable. You can never actually find that shortest program. So both of these frameworks, they miss the one physical constraint that binds every real agent. The observer, our GPU, has a finite computational budget.
So if the shortest program exists but takes 1 million years to run, for all practical purposes, that data is just random noise to us.
Exactly.
So if the problem is that we're time limited, how does this paper formally weave time into the definition of information?
They define something called a time-bounded probabilistic model, or PTO. You can think of it as a neural net architecture plus its training budget. It runs on a universal Turing machine, but, and this is the key part, it must stop within a fixed time function, $t.
So T is the computational budget.
T is the budget. So the program isn't just a description of the data, it's a time-limited description. And they use the minimum description length principle, MDL, as the core metric.
Okay, so the time-bounded MDL.
Yeah.
It minimizes the total cost to describe the data, $6. And that cost has 2 parts, which is what's so clever about this.
Right. So if you think of MDL-TLers as the total size of your perfectly compressed file for some data set.
And the first part of that file, the pipeline term, is the length of the optimal program itself. And that is epiplexity.
Yes. In your analogy, East dollars is the size of the really clever algorithm you had to write to find all the deep patterns to compress the data. It captures the learnable structural stuff.
And the second term, the expected code length, becomes the time-bounded entropy. So that's the leftover stuff.
Yeah.
The uncompressed junk that your algorithm couldn't figure out in time.
The residual noise, the unpredictable bits, yeah. And that split is the core idea. The best way to get the intuition here is to think about cryptographically secure pseudorandom number generators, or CSP-RNGs.
Right. To any observer with, polynomial time compute, the output from a CSP-RNG looks perfectly random. I can't find a short program to predict the next bit in time.
Exactly. So for you, that sequence has maximal time-bounded entropy. It looks like pure noise. But what's its epiplexity? It's its dollar?
Well, if I have the secret seed, the program that generates it is tiny. So its C-stellar must be negligible.
And there it is. The distinction is crystal clear. C-stellar correctly identifies learnable, reusable structure. If that structure is only accessible with infinite compute, then for us, for any real system, C-stellar is low and HGLR is high.
So the data might be simple to generate, but it's incredibly complex to model if you don't have the key.
Now we can use this framework to go back and resolve those paradoxes. Let's start with that first one, the idea that deterministic processes can't create information.
Yeah, this just flies in the face of modern RL. AlphaZero starts with the deterministic rules of Go, zero human data, and it ends up with this massive model that's just packed with rich, transferable knowledge. Where did all that information come from?
The resolution is that computational asymmetry we talked about. A deterministic function can dramatically increase the time-bounded information content, HT-taller or cellular, if the inverse function is computationally hard for the observer.
So it's not about how simple the input program is. It's about how hard it is for a bounded observer to work backwards from the output.
Precisely. They tested this with elementary cellular, automata, ECAs. These are just these tiny, simple rules that can generate incredibly complex patterns.
And they looked at 3 different rules, each one showing a different kind of behavior.
Right. Rule 15 was simple, periodic. It gave low H2 and low ACLers. Easy to compress, not much randomness. Rule 30 was just chaotic. It was impossible to predict, so it had very high HTT tier random noise, but low S-dollars because the limited observer couldn't find any reusable structure in the chaos.
And the really interesting one was Rule 54. It's complex, it's known to be Turing complete, and it generated a mix. It had medium HT and crucially high SE dollars.
And that highest S-dollar is telling us something very specific, that this deterministic process successfully generated structural content that the bounded observer could learn and compress. The recurring patterns, the little gliders, information was created.
But only because the observer couldn't afford the brute force approach of just running the simple simulation. It was forced to find a more complex structural shortcut.
And that leads us straight to paradox 2. The classical idea of symmetry of information, which says that the order you observe data in shouldn't matter.
But we know that's not true. I mean, any LLM practitioner knows that left-to-right prediction is way easier than trying to predict in reverse. Cryptography relies on one-way functions. Order matters.
And they prove it theoretically in Theorem 25. They show that if you use a one-way permutation, the time-bounded entropy is non-symmetrical. But the empirical evidence is even better.
The chess experiment.
The chess experiment. They took Lichess games and trained a model on the exact same data, just factored in 2 different ways. The forward order was normal. You see the moves, then the final board state.
Simple, direct computation.
And the reverse order flipped it. You see the final board state, and you have to predict the moves that led to it. It forces this complex inverse inference task.
Reconstructing the past.
And what they found was that the reverse order resulted in much higher H-dollars because it was harder to predict. But critically, it also gave a much higher epiplexity, SS-dollars.
So the model was forced to develop a richer, more transferable internal representation of the board state.
A mental model.
A mental model, yeah, of how this final state could have been achieved. Right. And that translates directly to more structural learning. That's a huge implication for data engineering. It's not just what data you use, but how you sequence it.
Which brings us to the last and maybe the deepest paradox, the question of induction. The old view is that likelihood modeling is just distribution matching. So if the process that generates the data, Q, is simple, then the best model, P star, should also be simple.
But that doesn't feel right. It clashes with what we see in machine learning, with emergence and induction, where the learned model, the giant pile of weights, seems to encode knowledge that's way more complex than the training inputs.
The resolution is that a computationally limited observer, in its struggle to maximize likelihood, often has to extract more structural information than what was explicitly there in the simple generative process.
They use a great analogy in the paper, The Murder Mystery. The killer is known to the author, the generative process Q. That's simple. But the model, the detective, has to induce who the killer is based only on the evidence in the story. It has to infer all these hidden variables.
And they showed this with that chaotic Rule 30 ECA again, but this time with hidden inputs. The model's loss converges to the theoretical minimum, sure, but the compute it needs to get there grows exponentially.
Because it can't just simulate the simple process, because the inputs are hidden from it. It's forced to build these really complex, resource-intensive predictive circuits to fill in the blanks.
And those circuits are the structural information. They are what makes STDAL shoot up. The model has to become smarter than the simple process that created the data just to do its job of prediction.
This also perfectly explains emergence. If you think about Conway's game of life, the local rules are dead simple. But the high-level patterns, the gliders and spaceships, are incredibly hard to predict just by simulating the local rules.
Right. An observer with infinite compute could just run the simulation for 1 billion steps, no problem. But a bounded observer can't afford that.
So the bounded observer is forced to learn the high-level concepts instead. It has to learn about gliders, their properties, how they collide. And that means building a larger, more structurally complex internal program. Higher C's dollars.
And they showed this again with the Rule 54 experiment. As they gave the models more compute, CST dollars went up and up as they learned more sophisticated emergent rules. But then they hit a critical threshold.
What happened?
A specific type of model, a looped transformer built for brute force simulation, suddenly became the best option, and CC dollars just plummeted.
Because the model no longer needed the complex emergent shortcuts. It could finally afford to just run the simple short generative rule.
Exactly. It's strong evidence that emergence high ST dollars from a simple generator is fundamentally a product of computational constraints.
Okay, so S dollars is clearly this measure of reusable, internalized structure. But if you're an ML engineer, how do you actually estimate it? Can't be another one of these incomputable things.
No, thankfully. They give 2 practical paths. The first is a heuristic from prequential coding. You basically estimate SI dollars by calculating the area under the training loss curve, but above the final loss value.
That area represents the total information the model absorbed into its weights during training. That's actually super implementable since we all track loss curves.
Totally. The more rigorous way is requential coding, which is about the cumulative KL divergence between a teacher and a student model. It's more complex, but thankfully both methods seem to rank data sets in the same way, so the simple one is a good proxy.
And the proof is in the ode pudding. They went back to the chess task. We know the reverse order gives a higher S dollars. What happened on a transfer task?
The models trained on the higher SD dollar reverse order data did significantly better on a hard ode task, cent-upon evaluation. That requires a deep structural understanding of the board, not just move prediction.
So higher epiplexity directly led to richer, more transferable representations.
Which concerns you can use S dollars as a metric for data quality, not just for models.
And this connects everything back to why today's LLMs are so successful. They ran a big analysis on different kinds of natural data. Language, chess, images.
And the results show this really important asymmetry. Language data, specifically open web text, have the highest estimated epiplexity by a country mile.
And images.
Images, CFR5M, had the least. Over 99% of its information content was classified as just time-bounded entropy, basically residual noise.
So why does it make sense that language is so high in SECT dollars?
Well, think about it. Language is this recursive, compositional, hierarchical system. You can always combine simple building blocks, words, grammar, to create infinitely new, complex, but still structured meanings. That structure is incredibly reusable.
Whereas a random patch of pixels in an image doesn't have that deep compositional structure. It's mostly just H dollars.
Which perfectly explains why language pre-training gives you these general capabilities that transfer everywhere. Robotics, math, while image pre-training just doesn't give you that same universal lift. Language just contains vastly more reusable structural information.
And they even connected this metric to an existing strategy, adaptive data optimization, or AD. That's a technique that picks data that lowers training loss fastest, and it's known to improve ode performance.
And it turns out what ADO is doing, probably by accident, is selecting for data that maximizes the estimated STLers. It just reinforces that epiplexity is the objective metric we've been missing for data quality.
So epiplexity really is this theoretical bridge. By putting computation on equal footing with information, we can finally reason about induction, emergence, and the real value of data.
We can move beyond just perplexity or simple scaling laws. It opens the door to developing a compute-aware version of classic ideas like sufficient statistics or information bottlenecks, moving past those old PAX-style measures that only care about sample complexity.
So to wrap up, here's a final provocative thought to leave you with.
For natural data, so the physical world we all live in, the simple brute force solutions like modeling the weather by simulating every single particle according to the laws of physics are almost certainly computationally inaccessible to any real observer, to us.
So we are forced to operate, always in a high epiplexity world.
Always. Which means that the definition of intelligence might not be about how simply the world is generated, but about how skillfully we, as limited observers, can extract and internalize that reusable structural information under these very severe time constraints.